Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's lecture, we will start discussing about a new problem in quantum mechanics that can be exactly solved. If you remember, the previous problem that we took up was the particle in a box problem. In that problem, we had the potential energy which was a discontinuous function. If you remember, we defined the potential energy in the particle in a box as to be 0 within the box and infinite outside the box. So, that means the function was discontinuous at the boundary, that was one, and the second point is that within the box the potential energy was constant. Now, today in this lecture we will deal with another problem which is harmonic oscillator, where the potential energy is actually a continuously varying function of the coordinate. When you discuss about harmonic oscillator, so the first difference is that here in this problem the potential energy is continuously varying function. The second point that we will discuss is that when we say harmonic oscillator, we have often a simple pendulum or a spring in mind. Suppose let us consider that we have a spring attached to a fixed surface at one end, and on the other end we put a load of mass m. Given the stiffness of the spring, we will have an initial length of this spring, let us call this x0. Suppose I pull this mass downward. When I pull this mass downward, what you would experience is that there is as if there is a force within the spring which is actually pulling the mass upwards. If I push this mass upwards instead of pulling it down, you would also experience as if there is a force inside the spring which tries to push the mass down. That means in this spring we have an inbuilt force which opposes the external force, or in other words which tries to restore the initial configuration of the spring, the initial length of the spring. So, that means when you try to elongate this is the spring would try to shrink, so that it comes back to its original position. When I try to shrink the spring would try to elongate, so that it can come back to its original position. So, as if there exists a restoring force in this spring. So, the second point that we should keep in mind is that we are dealing with system where there exists a restoring force, and if you follow this discussion that we had, this restoring force is opposite to the direction of the displacement. So, therefore, I can write this equation, this minus sign multiplied by x, which is the dimension along which I am stretching or shrinking the spring. So, this minus x suggests that the restoring force is against or in the opposite direction to the displacement, and this k is often a force constant, or also called as a spring constant. Depending on the stiffness of the string, or whether the spring is stiff or weak, the value of this k or the spring constant would change. Now, this restoring force makes this system a harmonic oscillator. How? Suppose you would imagine, instead of when I pull this mass downwards and then I release this mass, you would see that the spring would actually first shrink, it will come back to its original position, and the moment it reaches its original or equilibrium position, the direction of the force will change, and then you will see that it will start shrinking further, and then again after some times it would come back to its original position and relax, stretch a bit, and it will continue this motion. If the spring has no other way to dissipate its energy, you can imagine that this back and forth motion will happen for forever. So, this motion, this back and forth motion is what we call the oscillatory motion, that the system goes back to its equilibrium position by shrinking and stretching. Now, this harmonic oscillator, the way we defined this problem is a nice physical problem, but how does it relate to chemical worlds? One particular thing that we have in mind when we discuss harmonic oscillator is that the molecules that we deal with in chemistry, these molecules at a finite temperature are always under constant some sort of vibration. Now, these vibrations with these vibrations, the molecules always stretch or shrink along their equilibrium position. So, therefore, molecular vibration is a natural place of application for this harmonic oscillator. Apart from molecular vibration, you can also imagine any other system where the system has an inbuilt restoring force that brings it back to its equilibrium position all the time. In any such problem, we can use the problem of harmonic oscillator, and the solution that we will derive from this discussion can also be used in all those problems. One particular example is that when we use when we expose a molecule in external electric field or magnetic field, the molecular response to these fields can also be treated with harmonic oscillator problem. Before we start discussing the harmonic oscillator problem in quantum mechanical sense, let us refresh our idea or refresh our knowledge on the classical mechanical solution of harmonic oscillator. While discussing this classical harmonic oscillator, we would start our discussion with the equation just we wrote down, that the restoring force is negative of force constant k into x. But I know from Newton's equation of motion, force is mass into acceleration. So, therefore, I can write and now I have a differential equation I have a second order differential equation whose solution I already know. I provide a general solution to this differential equation as a sum of a sine function and a cosine function, where this omega I have defined as the square root of k over m. Now, this is the general solution. What is known here and what is unknown here. So, of course, the t is the time variable that is coming because of this differential equation. Omega is related to the spring constant, since I am discussing a particular harmonic oscillator. So, therefore, I know the value of k, the spring constant, and also since I know the mass of the system that I am dealing with. So, these two quantities and therefore, omega, they are defined by the problem at hand. What is unknown in this equation is that I have this a and b whose values I need to determine. I can, since I know this is the general solution of x, I can also write the general solution of the velocity, which is the first time derivative of x, which will come out to be a omega cosine omega t plus forgive me, this would be minus b omega sine omega t, because when I differentiate this cosine function with respect to t, I would have a minus sign. minus b omega sin omega t. So, I have now these two general definition of the speed and the position. I have now to discuss the boundary condition, the initial value condition. If you remember, when at time t equals 0. So, when I started my exercise at time t equals 0, x at 0. So, I put t equals 0 in this equation. So, when I put here, so this term becomes sin 0. So, which is 0 and this term becomes 1, cos 0 is 1. So, therefore, x of 0, that means the position at time equals 0 is the value of b, and I define that as x 0. X 0 is the equilibrium position or the starting position of the system, of the oscillator. So, I already have an idea about what is the value of b here. B is the initial position x 0. Now, I would apply the same t equals 0 system situation for the speed. So, the speed v equals 0, if I put t equals 0 here. So, I will get cosine 0, which will be 1. So, therefore, I have a omega, and then when I put 0 here in this place. So, that this will give me a sine function which will be a 0, which will be 0. So, therefore, I am left with v of 0 is a omega. But I know that the beginning the spring was at rest. So, therefore, the initial speed was 0. So, therefore, I will make this 0, and since omega is related to the spring constant and the mass of the body. So, therefore, this is not 0, that way I have a is 0. So, I now have an idea about what is the value of a and what is the value of b. Let us use the knowledge that we have now and define my x of t as a, which is 0. So, therefore, this term vanishes, b is x 0. So, x 0 cosine omega t. So, this is the general definition of the position that I am getting for a classical harmonic oscillator. All right. And what about v? V at any time t will be given by, when I apply. So, in this equation a is 0. So, this term vanishes. So, I am left with x 0 omega, sorry, there is a minus sign, minus x 0 omega sin omega t. Now, we will discuss what is the value of the kinetic energy. Since we already know the velocity or speed, kinetic energy is half m v square. So, if I know v, I would simply use x 0 square omega square sin square omega t. This is my kinetic energy, but if you see omega is k over m under square root. So, omega square is going to be k over m. So, this m and the other m will cancel out, and then I will be left with half k x 0 square sin square omega t. Now, what about the potential energy? The potential energy, we know that force is the negative gradient of, since I am dealing with only one variable, negative gradient of the potential energy is force. So, therefore, minus dV by dx, where V is capital V is the potential energy, dV by dx is force is minus kx. So, therefore, V or dV equals kx dx, and when I integrate both sides, I would get the potential energy as half k x square. And what is x? I know x is given here. So, I get half k x 0 square cosine square omega t. So, now this is my potential energy of the harmonic oscillator and this is my kinetic energy of the harmonic oscillator. If you see, the potential energy of this harmonic oscillator is a square of a cosine function. The kinetic energy of this classical harmonic oscillator is a sine square function. If I add the kinetic energy and the potential energy, you would see that half k x square x 0 square sine square omega t and then cos square omega t. So, that the total energy E will be the sum of the kinetic energy plus the potential energy. You see that this comes out to be half k x 0 square. Now, this energy is independent of time. So, what do I see? That I see that the potential energy and the kinetic energy will be an oscillatory function, but the sum of the energy is going to be constant. So, if I plot the results that I obtained here, so suppose this is my time axis and this is my energy axis, the potential and the kinetic energy will be a sine square function. So, this is the sine square function and then this will be the kinetic energy and the potential energy is the square of a cosine function. So, now the sum of the two, the kinetic energy and potential energy, you will see that will be the, when I take the sum, this will turn out to be a constant. So, the thick line is your kinetic energy, which is a sine square function. The dashed line is your potential energy, which is a cosine square function, and this constant line is your total energy. So, this is what we know about the classical harmonic oscillator. Now, we would continue our discussion for the quantum mechanical treatment of this harmonic oscillator. Now, if you remember, when we said that if we want to solve a problem quantum mechanically, we have to see, if you remember the postulates of quantum mechanics, it says that everything that we need to know is there in the wave state function, the wave function, and if we want to know anything in particular about that system, we must use the operator corresponding to that observable. Since we are interested here in this case to learn more about the energy of this harmonic oscillator, so therefore, what we would do is that we would start with the Hamiltonian of the quantum mechanical oscillator. So, we would write down the Hamiltonian of the quantum mechanical harmonic oscillator. So, Hamiltonian would have, which is the operator for the energy, has two components. One is the kinetic energy, other is the potential energy. The kinetic energy operator here is p square by 2m. This hat, if you remember, is a way to signify suggest that this is an operator. So, we know that kinetic energy is momentum square divided by 2m. So, we are going to use the operator corresponding to the momentum operator here, and we already have seen the potential energy V equals half k x square. We do that by using that the force is the negative gradient of the potential energy. So, we have half k x square, where x is the position operator and k is the spring constant. So, the k now we have, we will come back to this definition. So, this is the two operators that I have in the Hamiltonian operator, and to obtain the general solution for this Hamiltonian. So, I have to write down the Schrodinger equation corresponding to these two operators and solve the problem. In many textbooks, you would find the quantum mechanical solution of this problem is obtained by writing down the differential equation and then solving, going through the algebra and finding the solution. While that provides a rigorous way to treat the harmonic oscillator through quantum mechanics, we will actually use a slightly different approach. This approach will help us refresh our understanding of quantum mechanics by dealing with the terminologies that we have already defined. To do that, instead of solving this problem in terms of the standard potential, the momentum operator and the position operator, what we will do is that we will redefine this Hamiltonian in a slightly different way. So, before that, let us define two new operators. I call this operator A plus, and I define this operator as beta by square root over 2 square root 2 and I define another operator A minus, which is defined as the operators may appear to begin with, they may appear very scary, but nothing to worry about them. You see, I have defined only one new things, that is beta. So, I define my beta as beta square equals m omega by h bar. So, I know the m, which is the mass of the system, omega is given by square root of k over m that we have already defined, and h bar is the Planck's constant h divided by 2 bar. So, this is just a constant for a, so this is a universal constant and m omega are constant for a particular problem. So, therefore, beta square is a constant and beta is a constant. Now, if you leave aside beta, then you see that there is a position operator and then there is momentum operator, and these two operators we already know. You see a slight a somewhat different way of writing this operator, which should be clear when we do a few more steps of algebra. So, now we see that we have defined two operators A plus and A minus in terms of x and p. So, our Hamiltonian had p operator, the momentum operator and the position operator, but instead now we have A plus and A minus, two different operators which are expressed in terms of x and p. Since they are A plus and A minus are expressed in terms of x and p, so I can of course re-express my x and p in terms of A plus and A minus. If you see, if I add this A plus and A minus operators, the second term in these brackets, they will cancel out, then I will be left with only x operator. So, this is what I show you. So, the operator x is simply A minus operator plus A plus operator divided by square root of 2 beta. So, you can rearrange these two equations to obtain here. Similarly, I can write down operator p as A minus operator minus A plus operator divided by so when I do A minus and A plus, you would see that I will be cancelling out x operator and then I will be left with only p operator. So, this is what I would get for x and p. Now, if you recall, we started defining our Hamiltonian in terms of the momentum operator and the position operator. We defined two new operators A plus and A minus in terms of x and p, and now we are saying that x, we are also defining x and p in terms of A minus A plus. What is the advantage? The advantage is that now we will apply this, use this x operator and p operator in this equation and rewrite this Hamiltonian, but in this case the Hamiltonian will be written down, since we are replacing x with A minus A plus and p with A minus A plus. So, therefore, the Hamiltonian will now, if you rearrange, it would come out to be So, the Hamiltonian would be expressed as h bar omega a plus a minus operator plus half. This is very easy exercise to show, and what we would do is that we will discuss in the next class as to how we can solve this Hamiltonian. So, what one thing that we did is that instead of expressing, we started by expressing our Hamiltonian in terms of the position and momentum operator, but we converted this position and momentum operator in terms of two new operators, a plus and a minus. In next class we will discuss also what are the significance of these operators, but one advantage is that what we obtained here is that we expressed now Hamiltonian in terms of these new operators a plus and a minus, and what the solutions would come out of that will be discussed in the next class. Thank you for your attention.